So let me write it down here. P dependence in FL P lambda n m due to non-1pi contributions in connected brains functions. Okay. Now recall, let us we will now simplify our consideration a little bit by going into the 1pi vertices. So recall that GCE x1 to xe is given by an expression of this sort: -1 I over h bar integral du1 to ue, then gc2 x1 u1 gc2 xc ue times gamma e u1 to ue plus other contributions. So this is a 1pi vertex, and these contributions are coming as they are written as tree-level diagrams involving. So these are tree-level diagrams involving gamma e prime with e prime less than e. So this means, we know we had studied this 2-point function also, this GC2. It is this has contribution from 1pi 2-point functions. So that is like so therefore the entire connected Green's function is given in terms of 1pi vertices that either gamma 2, which are sitting inside this, and higher gammas which come as vertices. So all information are contained in 1pi vertices. The 1pi by which when I say 1pi vertices, they are not only 3 and higher vertices, but also 2 vertex, I mean, which gives you the total net propagator. So they are also 1pi diagrams. And so let us look at what the structure is for 1pi vertices. That will be studying that will be enough for us. So gamma e p1 to pa this let me write it down that way. So this is position space. It's given p1 to d pe e to the power I p1 dot u1 dot ue gamma tilde p1 to pe, where this gamma tilde has a loop expansion L equal to 0 to infinity f lambda m, that doesn't depend on doesn't depend on P, I guess F of lambda that doesn't depend on M as well, because there are no propagators, tree-level propagators, and then I, L, comma, N. P dependence, it could have a P dependence if the, so this will involve a P dependence. Can come from derivative interactions. So if you have an interaction where derivative of phi is involved, we are considering polynomial interaction, which is a phi to the power something, but instead of that, if we had phi derivative of phi involved, then that vertex factor will depend on P in momentum space, Feynman rules. And so since F is a function of the vertex factors, so that P dependence, because the vertex depends on P, that P dependence would come in F. Otherwise, since we are considering polynomial interactions, it is in P independent. And this ILN has the same structure. As we discussed, so ILN is given by the same product over j equal to 1 to L dLj minus infinity to plus infinity, product over k to capital N. Okay, now we should basically now what we have to do is to understand the divergence structure of this, the claim, the a priori claim that we have made, that this has divergence, and we have to see how exactly this divergence is appearing, what we mean when we say that it has divergence. And to see that, we will introduce what is called Feynman parametrization. So that we are doing to see divergence structure. Consider complex numbers A1 to AN such that the convex hull of these complex numbers on R2 on the complex plane does not include the origin. Okay, what is a convex hull? A convex hull is the smallest convex set in R2 that contains these n complex numbers. Smallest convex set on the plane containing A1 to AN and the meaning of convex set is that the line containing connecting any 2 points out of these n points in this set passes through the set. So convex set means it's a convex set that corresponds to this A1 to AN is a set such that if you connect 2 of these points A1 to AN, then that connecting line will stay within that set. The line connecting any 2 points in the set. So the set given by A1 to AN is such that if you take any 2 points within that set, the line connecting those 2 points will be within the set. The set passes through the set. So here is it's a simple thing to if you just picturize it. So suppose I have 5 points A1, A2, A3, A4, A5. Then I have to find. So let me show this. I have to find the convex hull of this. So that it's a convex set. So convex hull, for example, suppose I take this. I mean, I am suggesting pictorially what I'm trying to do. Suppose I take this region, then you see any 2 points if you take, because it's a convex, it is convex. If you take any 2 points, connect them within the set, this entire line is within the set. That is not true for a concave set. If you take this, then this point and this point will be connected by a line which is outside the set. So convexity means that. Convexity means this is what we usually mean by what convexity is, which usually call this structure convex, and the mathematical criteria for that is that if you take 2 points within the set, line connecting those 2 points will remain entirely within that set. Then it's a convex set. So so convex hull is now this is not the convex hull, because I can actually satisfy convexity if I just connect them by a straight line instead of a convex line like this. I can connect them by a straight line. So if I connect them by a straight line, that is the smallest one. Of course, this is also a convex set. I mean, of course, this is convex for this one, but if you take this, you have to make sure that 2 points should not go outside this. So anyway, the smallest criteria will tell you that I should connect them by the straight lines on the complex plane. I'm talking about R2, not a more complicated space. Then you could not afford to make it concave because of the convexity requirement. So this is the minimum you have to do, and then it's a then this criteria is fulfilled because of this, because they are connected by straight lines. If you take any 2 points within this set, the line connecting them will always be within the set. You cannot draw a line that goes outside the set but still connects 2 points within the set. If you draw a line that is outside the set, that goes outside the set, it connects outside points, not the points that are inside. Okay, so this is a convex hull. Now, the condition for Feynman parametrization, the statement is that you could take such n complex numbers such that within the convex hull, the origin of R2 or the complex plane, origin of the complex plane does not sit inside anywhere within the convex hull. It is in the under this condition that the parametrization that we are going to talk about is valid. Okay. Now let me specify some results, some mathematical results, and then I will argue why they are right. And that mathematical result is basically Feynman's parametrization. So one over a1 to an is so inverse of product of inverse of n complex numbers is given by gamma n times d alpha 1 to d alpha n 0 to 1 Dirac delta 1 minus sum over k equal to 1 to n alpha k divided by alpha 1 a1 to alpha k alpha a n to the power n. Let me call this the first result. And there is a more general result, which we will, I'm just specifying it for completeness. But for this lecture and this next one, we will need only the first result, not this one. If you have powers of those complex numbers, so P1 to Pn are the powers, then the result gets modified in this fashion. This is the result. Let me call this number 2. Of course, if you set and gamma n is n minus 1 factorial. Of course, the second result, if you set P1 to Pn all to be 1, then you get first result. So, so these Pi's are positive integer. Okay. So let us focus. Let us first focus on number 1. Number 2 is more complicated, but for number 1, we have a simple pictorial description of it. Let's take n equals 2. There are two complex numbers, 1 over a1 times 1 over a2, and correspondingly there are two real parameters, alpha 1 and alpha 2, both going from 0 to 1. Okay, and it is the inverse power of that combination alpha 1 A1 plus alpha 2 A2 is what is being calculated. So this because of this delta function, this alpha 1 plus alpha 2 must be same as 1. So alpha 1 plus alpha 2 must be 1. So that is a condition. So then alpha 1 plus alpha 2 equal to 1 line, straight line is this one. Okay, similarly, if you take the convex hull of these two points, so this is complex plane, yeah, and suppose this is A1 and this is A2, then the complex hull is nothing but the straight line connecting these 2 points. And there is a one-to-one map between this line and this line, which is given by alpha 1 A1 plus alpha 2 A2. So when in the integration, when you go, when you do the integration over this line, because you are doing an integration over alpha 1 and alpha 2 with the restriction that alpha 1 plus alpha 2 equal to 1. So you are basically, when you do d alpha 1 d alpha 2 integral, that apparently seems like a two-dimensional integral over this plane, but that is not true. Because of the delta function, your integration is restricted to this line. As you are moving in this line, you are moving here from A1. So if you look at the combination, it is alpha 1 A1, then alpha 2 A2. So when you start from alpha 1, alpha 2 is equal to 0, and that this thing is only A1. So when you are, this point corresponds to this point, and as you are moving along this line, you are going along the convex hull of these two complex numbers. So this is the convex hull. Similarly, if you take n equals 3, you have a three-dimensional space, alpha 1, alpha 2, and alpha 3. And this is the plane contained within this triangle. That's the points on that satisfies this equation alpha 1 plus alpha 2 plus alpha 3 is equal to 1. So it's a three-dimensional space in which you have an equation alpha 1 plus alpha 2 plus alpha 3. Locus of this equation will be a two-dimensional space, which is this blue colored slice. And if you look at this, the complex plane, on the other hand, you have three complex numbers A1, A2, and A3, and the convex hull is this triangle in the complex plane. And the map, this map is alpha 1 A1 plus alpha 2 A2 plus alpha 3 A3. So alpha parametrization means that when you integrate over alpha, you are actually integrating over the convex hull of this of those three of these n complex numbers. So when you said both alpha 2 and alpha 3 to 0, then and alpha 1 must be 1, and this point corresponds to A1 according to this map. Alpha 1 is 1, alpha 2, alpha 3 0. That's A1. So this point gets mapped to this point gets mapped to this point, and alpha 2, this point gets mapped to this point, and these lines get mapped to these lines, and so on. Okay. And since in this parametrization the result has the map sitting in the denominator with a power, there is of course is a risk of divergence if the origin will be included in the convex hull, because the integration is running over the convex hull. If the integration region is here, then for this point the denominator will go to 0 with a power of n, so that will diverge. So that is not that then this identity breaks down. You have to make sure that A1 and A2 are not in the convex hull. The origin is not in the convex hull of this complex number. So let us now prove the identity 1. Okay,